Now we're going to talk about the principle of superposition for electric field and then a little bit about the voltage. So we know that the electrical force is equal to Coulomb's constant times the charge 1 times charge 2 divided by the distance square. Let's say that here we have Q1, Q2, and now we have Q3, and we want to know what is the electric field at this point. So the electric field due to this charge at this point is the force divided by Q3, in which the force is Q1, in this case times Q3. So the electric field would just be K times Q1 divided by, let's say, R sub 1 square. This is the electric field at this point due to charge 1. The electric field at this point due to charge 2. So actually we don't need this Q3 anyway. Would be just K times Q2 divided by R2. So the principle of superposition that we see in many fields is that the electric field at this point, at the point P, is equal to the electric field at this point due to this charge, plus the electric field at that point due to this charge, and plus the electric field at that point due to any charge. But let's say that everything is neutral and we just have these two, then it would be this. This is the principle of superposition. And so let's say that we know that for a positive charge, let's say if this is positive, the electric field is going out, so it's away. So here's how we draw the electric field of a positive charge, and for a negative charge is the opposite. Here's the negative charge, and so the electric, actually these are called electric field lines, are drawn like this. They're going towards the negative charge, and we know that this opposite charge attract. So if, for example, I have here a charge and this charge is negative, this would be repelled by this one, but would be attracted by this one. So the if this is very far away of these two charges, then these two charges will behave as just one point. For example, if this has 3 coulombs, plus 3 coulombs, and this negative 2 coulombs, this would behave as just if there were just one charge with 1 coulomb, and then the electric field would be, well, that the constant times 1 coulomb divided by the distance, but this distance is far away as the distance between these. But if we are talking about a small distance, like for example this, there is a point in which this charge would be not moving because it wants to move, or it tends to move in this direction because of the repulsion here, but it tends to attract to this one because of the difference of charges. So there is a point in which there will be no repulsion and no attraction, that they both will cancel. In this case, because this is, well, I have drawn it actually vertically or rectal, that would be, I don't know, some point here. Well, in that point, when that point happens, that is like the Lagrangian point, or the equivalent of the Lagrangian point that is seen in planets when we have the attraction, that we have one between the Earth and the Sun, another after that. But started when the gravitation of the Earth and the Sun are maintained. So if we have a point or a mass at that point, there will be no acceleration towards the Earth or towards the Sun, because the attraction between that mass and the Earth and the Sun are the same. So that is the exactly the same thing here. If now we just have, let's say, this, and these are the electric field lines. Here we have a charge. Actually, the charge, let me put it here. Here I put the charge. If I release the charge will move towards this line, towards the electric field lines that it belongs, and the voltage, that is the electrical potential. Electrical potential means the electrical difference. This is not electrical potential energy. The voltage, as we will see later, is the electrical potential in relation to the distance, and the voltage is, for example, here, the voltage between this charge and this, or between this point and this point, is, let's say, the same as this, or as this, as this, as this. So we can draw like a contour surface, like is made for temperature or for altitude. Here, this is our contour, and this is a contour of the voltage. So here I have another level of voltage, and here another, but all the voltage here is the same, because as we will see later, the voltage is equal to the line integral of the electric field of dl, and this is the negative of the constant, negative of Coulomb's constant times the charge divided by r, not r squared but r, and here we have the same r for all these. So this is a contour for the voltage, and these contours are always perpendicular to the electric field lines. In vectorial fields, when we want to represent the density of a vector field, that means, for example, more close to the charge, the electric field is greater, because here we are dividing by, here it's just divided by q, and so we have the electric field. We are dividing here by r squared, or r, for r squared. So if the distance is small, now I'm talking about the electric field, not the voltage, the electric field. If the distance is small, well, also for the voltage, but the voltage change with the inversely direct to r, and the electric field change inversely direct to the square power of the distance. So if the distance is small, then I have a higher electric field. And so if we get closer to this charge, here for example, we have these electric field lines, and we see that if we take a volume, for example here, or a surface here, we have that the density is greater than if, for example, I take it this same volume here, where I just take, for example, one electric field line. So the magnitude of the electric field is drawn like in this, when we draw the electric field lines this way. As we get closer to the charge, we have higher electric field is wrong as the density of the electric field lines that are going out of the charge or going in for a negative charge.